recap for the sake of the notes, looking for where the function is increasing. I asked you then where is it decreasing. What I'm trying to make a point of now is that when we talk about intervals, we're talking about input values. So we need to identify the input values where the interval is positive and where the outputs are decreasing in value. So again, we have two of them. We have this arm and we have this arm. Now, what's this got to do with what we're talking about in calculus? The whole semester so far, we've really talked about one topic. What is that? Derivatives. Okay? So now the question could be, a big so what? How does this discussion of increasing and decreasing portions of the function connect with our discussion of derivatives? What would you say about all of the tangent lines? If we were to take a tangent line, well, let's see, we could actually do that, I guess. Let's take a tangent line here. I'm going to attach it someplace right about there. And then what I'm interested in is the, with derivatives, we take tangent lines and we're interested in their slopes. So let's take a slope of that tangent line. We'll put it right there. And we'll make that tangent line just a little more prominent. If I take this tangent line, the point of tangency, if I can, come on. There we go. So we don't lose track of what this means. Okay. If I take that tangent line, that point of tangency, and I move it anywhere along this portion, what's the same about that tangent line slope? It's negative. It will remain negative until I get to where? The what? Until I get down here to -1. And then somewhere in here, it's a little hard, that's supposed to be 0. If you look at that, it's a negative, it's in scientific notation. And then I move that point along here, what's happening to the derivative? Positive. The slope of the tangent line is positive until I reach this turning point, whatever that turning point is, and then I get 0 again. And then the derivative, the slope of that tangent line, becomes negative again until I come all the way back down to here, and then I get another minimum, and I can start going up again, and it's positive. So the derivative can tell us something about the shape of the graph, the direction, the characteristic of the function, where it's increasing and where it's decreasing. So if the first derivative is positive, the slope is, I'm sorry, I said that wrong. If the first derivative is positive, the function is increasing, and if the first derivative is negative, the function is decreasing. What happens at these very special points down here between increasing and decreasing? Can't seem to get it to stay there. Okay, so if I know that I have negative slopes and I have positive slopes, and I'm on a continuum between positive and negative, what is right there between positive and negative? 0 is there, which means that the slope of the tangent is 0. So I have some control now over finding derivatives, especially derivatives. If I find derivatives that are at some kind of a peak here, we call these extrema. There we go. Extrema, the slope is 0. Now, again, it doesn't look like it's 0 there, but it truly is. If I take to the negative 10 to the negative 6 power is close enough. Okay, let's go to our notes then. Increasing and decreasing functions. Again, when we talk about increasing and decreasing functions, which part of the function are we talking about? Inputs or outputs? Output values. Okay. So the increasing and decreasing output values of a function is what we really should be saying. Here are some tests for increasing and decreasing functions. Let f be a function that is continuous on a closed interval. Okay, and continuous, no gaps. You can draw it from left to right on a closed interval from A to B, and differentiable on the open interval from A to B. So the function is continuous and the derivative is defined for all of those. Similar to what we have here. This function is continuous and it is the derivative is defined. We don't get any point here where it says that the derivative is undefined. So the derivative is defined everywhere. Okay. And now we're talking about an interval, so definitely if I decided on an interval, we could do that. If the first derivative is greater than or equal to 0, what's another word for greater than or equal to 0? If something's greater than or equal to 0, how about positive? If the first derivative is positive for all the inputs in the interval from A to B, then the function is increasing. In other words, the output values of the function increasing on that interval. So if the first derivative is positive, function is increasing. Tangent lines are going uphill. If the first derivative is negative, then you know that the function is decreasing. So we would have tangent lines that go downhill because the slopes of them are negative. Up here we'd have tangent lines that go uphill because the slopes are positive. And if the first derivative is 0, then the function is constant on that interval. So if for all of those inputs in that interval the derivative is 0, now that's not going to happen that much that we have a horizontal portion of our graph. But what we're saying is that if the first derivative is 0, it's neither, and maybe we should put that in, neither increasing or decreasing. Okay. So the first derivative is going to be now our way of determining a lot about these graphs. Again, chapter 3 is a lot of visual, it's a lot of graphing information. I'm looking forward to actually the last section in this chapter because it talks about optimization and we get into more of the applications that is relevant to what you're about, and that's the business field. Okay, well let's look at the next problem. It says use the derivative to identify the open intervals on which the function is increasing or decreasing. Use the derivative. Well, the first thing we have to do is to actually determine the derivative. Okay, are you needing to go back to see something? No? Okay. So use the derivative on this. So the first thing we're going to do is write the derivative. It's one of the easier ones you've had to deal with. There's no composite functions, no products, no quotients, no chain rule. Four x cubed minus 4x. Okay. Use it to identify the open intervals on which the function is increasing or decreasing. If the function is increasing, the derivative is what? Positive. If it's decreasing, the derivative is negative. What's between that negative and positive? 0. If I know where the derivative is 0, then on one side it could be positive, on the other side it could be negative. If I know where the 0 is, if you go back to here, if I know where this is at 0, then if I look at the derivative of values less than that, and they come out to be positive values, then I know that the function is increasing. If I look on the other side of that horizontal tangent line point, and I choose a point greater than, an input value greater than the one that creates a 0 derivative, hence a horizontal tangent line, and I see that the derivative's value is negative, then I know that the function is decreasing. We're going to do that. We're going to find out where the function has 0 value, where the derivative, has 0 values. If I know where the zeros are, then I test on either side of those, and I can then determine if it's increasing on the other side or increasing on the other side of the point where it is 0. So let's see here. So the second thing we're going to do is set the derivative equal to 0. So I have 0 equals 4x cubed minus 4x. Use your algebra. We could factor out a 4x. Anyone try this? Factor out a 4x, and we have then 4x, the quantity x squared minus 1. If I know that product is equal to 0, and I have two factors, which factor is 0? Stephanie, which of those factors is my 0? Either one could be? Okay, because I don't know which one for sure. So if the 4x is my 0 factor, then that means x is 0. If by chance the x squared minus 1 is my 0 factor, then I've got x minus 1 and x plus 1. Which of those factors is going to make my product 0? Kevin, which one? X minus 1 or x plus 1? Mm-hmm. Either one again, yeah. So x minus 1 is 0, which means x is 1. Or, I'm not trying to trick you, I'm really not. Okay. Or x equals negative 1. So I end up with three values where x is equal to 0. Let's take our inspires, add a page, another graph page. And let's graph this function. I gave you x to the 4th power minus 2x squared. I'm going to change the window. So let's see here. I'm going to make it, we'll make it something like, how about negative 2 to 2 scale by 1, and, maybe negative 0.5 to 5 scale by 1. Choose what you want, but, we'll see if this works here. Oops, I guessed 2 wrong, didn't I? So let's do something else. We'll just make this one, we'll make it negative 1. That's too, I'm going to do one more adjustment. You guys can follow my lead if you want. Negative 1.5. There we go. Okay. Now, we're looking for where, let's see, it says use the derivative to identify the open intervals in which the function is increasing and decreasing. Do you see the function decreasing anywhere? Yep, right over here. Okay, all the way down to here. And then it's like the first one I gave you. Then we have a second one here. Increasing here and here. Between the decreasing and increasing, you've got a point where if I draw a tangent line, slope of that tangent line would be 0. Got one up here and got one down here. Where do you suppose, or what do you suppose the inputs are at those points? Take a wild guess as to where you think. Yeah, that's what I'm guessing too. Okay, so I'm going to put that right here, and I'm going to go in and, well, let's see, maybe it won't do this for me. I was hoping I could do a coordinate. Yep, it's doing a coordinate. Okay, so I'm just going to do coordinates there. And I'm going to, let's see, you think at -1? Because that's what we found. Okay, so right down there. You think at, what did you say, 0? Okay, so let's do it. That looks pretty good. And over here then at 1. Okay. Because we've used the derivative and we have found these zeros of the derivative, easy enough to find, we go over here and we can match up, and sure enough it's going to be there. Now the question is, what are the intervals of negative derivatives and positive derivatives? Well, again, if I look for a derivative between -1 and 0, it should be positive in value. Okay? And if I look for one between 0 and 1, it should be negative. And then over here would be negative and positive. So what we can do, and I can't remember now how your book presents this, so I'm going to give it to you in the way that I have in my notes, even though we've got the Inspire that could really help us out a lot. We're going to set up a table, and we're going to look at intervals. We're going to look at test values. It's a sign chart. I'll just put that up here. Sign table, sign chart. I don't know what name the book's using, but we'll call it that right now. We're going to look at the sign of the first derivative, and then we're going to have a line here for conclusion. Okay. So I've got now this, I've got on a continuum here, if I were to, let's pretend this is my number line, I could put down that, you know, let's say this is -1, this is 0, and this is 1 over here. I've got my number line now divided up into 1, 2, 3, 4 intervals. I'm going to go from -infinity to -1, from -1 to 0, 0 to 1, and 1 to infinity. These are, you might want to make that note. Are these inputs or outputs? The interval. Are we inputs? You might want to put that in if you're not sure. These are input values here. Okay. I'm going to test a value in this interval. I can choose anything. Is it true that any input value less than -1 would have the same sign on the derivative? Doesn't have to be a special one. Anything I want. Any input value between -1 and 0 is going to have the same value or the same sign of the derivative. It should be positive, and so forth and so on. So all you have to do is just choose anything. So we can choose, you know, an x equaling -2, an x equaling -1/2, x equaling 1/2, and let's just say x equaling 2. We're just going to test out a, you know, get a test value, one for each of those intervals. What's the sign of our derivative going to be in each of those? Well, what I'm asking for is, if I put -2 into my derivative, let's see, where's my derivative? negative 4x cubed minus 4x. If I put negative 2 in that, is my derivative going to be positive or negative? That's all I want to know. I don't need a specific answer. I just need to know, is it positive or is it negative? I could also put it in my factors here. So let's see, I like my factors better because if I put a negative, like a 4 times negative 2, and then a negative 2 squared minus 1, is my first factor going to be positive or negative? 4 times negative 2. Negative. Negative 2 squared minus 1. Positive or negative? Negative 2 squared. Positive minus 1. What's the sign of that? Now I need to let me do that for you and then you come back later. Okay, we'll do it. What's the sign of a negative times a positive? It's a negative. So the first derivative is negative. My conclusion is that f of x is what? Increasing or decreasing? Decreasing. The first derivative is negative, so the function is decreasing. Is that what we said over here? Decreasing? Yeah, exactly what we said. So I'm going to go up here now, and I'm going to use, there are my factors. I'm going to use that the factors again with negative 1/2. So 4 times negative 1/2 is 4 times negative 1/2, positive or negative? Negative. Negative 1/2 squared minus 1. Negative. Are you pleased? A negative times a negative is positive. Is that what we see over here? Yes. Okay, so we can choose any value we want. Now, I have to tell you, some of this work, like the sign chart, was extremely important to people like me when I was sitting in a place like you are. We had no calculator. We could not see a picture of this unless we did lots of points and then try to connect the dots in a reasonable manner. We couldn't just put it on a calculator and see a picture. And so it was really important that we had other ways of doing it. So the sign charts, a lot of good mathematics here, but the sign charts were extremely necessary to us. Are they as necessary to you? When you look at this, can you tell me where those are? You take the derivatives, can you look at this and see this is going to be negative and this is going to be positive? Yeah. So, a question that we now have is, how much of this do I really hold you to? Well, I hold you to knowing the idea that if you have a positive and a negative, it's a negative and so forth. I hold you to the idea that you need to factor this out in order to find these, I'm going to call them this already. They're called critical numbers. That's going to come up later on, but these are critical numbers. X equals 0, x equals 1, and x equaling negative 1. Those are called critical numbers. So if I continue on, oh, by the way, if the first derivative is positive, what do you know about the function? Increasing, right? Second derivative, or the next one, if I put 1/2 in there, 4 times 1/2 is positive. 1/2 squared minus 1, negative. Are we surprised that it's negative? No. Is the function increasing or decreasing? Decreasing. Do we see that on the graph? Yeah, all this stuff follows the graph. So if you do a combination of this, you should not have any trouble with it. Let's do one more just to make sure the notes are complete. If I put 2 in, my test value 2, 4 times 2 is positive. 2 squared minus 1, positive. Is the function increasing? Yes. Okay, so the analytical work, and again, I show this to you because I can't remember what the problems on homework look like, but I want you to have this. I want you to know how that sign chart looks. They may have you do sign charts on some of those problems, so this is what we're talking about. Okay, always connecting it with what we see on the graph. Okay. Here we go. I knew it was coming up. I've done this lecture for the Calc 1 classes, almost identical to this, but the way we say things in each class is a little different. So here's where you get the word critical number. Now I know the tendency is to want to write every single word down because you think the words are that important. They're not. It's the thought process we're going through. Critical number. Just remember that it's critical number. The function is defined at, is C an input or output? If f is defined at C, value C, input or output? Input, yes, an input. So if the function is defined at that input value C, then C is a critical number. There we go, critical number of the function if the first derivative is 0, and this is very important, if the first derivative is 0 or if it's undefined. Okay, if the first derivative turns out to be undefined, where it's undefined is also called a critical number. I don't know if you've seen many of those. In the other class we've seen them, but I don't know if we've seen very many undefined functions that have undefined derivatives. Okay. Guidelines.
So you're saying it's still a critical number?
Yes. Yes, it is a critical number. Now, let me just share with you that one of the ones, and I can't remember if we did that in this class or not, but if we have a function like this, we know that the absolute value function, we could see it, I guess. This value C, the derivative is undefined at that value C. The reason is, what's the sign of the slope of this portion? Negative. Okay, so the derivative as we approach C from this direction, the limit is negative. What is it on this one? Positive. You know, if you try to clap, you can't. Okay, so we say that the derivative is undefined because the limit does not exist at that point. And that's one of the reasons, one of the ways that the derivative is undefined. Okay, guidelines for applying. I want you to put all your pencils down. I don't want you to do this. If you want to know these notes, you can go back and find it, but this is too much writing for you to focus on that. Let's just listen for what we're doing here. Find the derivative. Did we do that? Yeah. Okay. Locate the critical numbers and use those numbers to determine the test intervals. Did we find critical numbers? How did we do that? Let me put it, I'll put it on here. Set the first derivative equal to 0. That's how we find and locate the critical numbers. Okay. Test the sign of the derivative at an arbitrary number in each of the test intervals. Did we do that? Back here. Remember I said use a test value. Anything that's in this interval, use it because it's true for all numbers in an interval. Okay, so we did a test value. And then use the test for increasing and decreasing functions to decide if the function is increasing and we did that. Okay, so all these words, you did it. Look at it later. It's in the textbook, but I don't want you to think. I don't want you to write that down. Okay, let's apply it. Find the critical numbers. Step 1. Take the derivative. What rule do we have to use? We're going to use that, but the first one we're going to use is, I heard it, product rule. Yeah, we have to. You got the product of x times the cube root. Now the first thing, actually the first thing I would do, yeah, I'll stop that in just a minute here. First thing I'm going to do, instead of taking the derivative, I'm going to rewrite this as x times x minus 1 to the 1/3 power. I'm going to rewrite it that way, because I know I'm going to have to use the 1/3 power. That's a cube root, in case you couldn't see it back there. Okay, now I'm going to take the derivative, and I am going to use the product rule. If you're not familiar with that, you need to be. So it is the first factor times the derivative with respect to x of the second factor plus the second factor times the derivative with respect to x of the first factor. We keep working.